So, we will look into now some concepts of flow system, because some of the services are flow systems. So far we looked into vertical transportation of human being, that is also flow, but then it's you are allowing people to flow, that is intelligent things to flow, not materials. So, now we will look into some of those other. So, services generally one can consider it as a flow system, right. So, so we will give some outline of the general service system. Then usually you might have storage, and of course, you might have diversity of usage. These are the concepts we discussed. Some of it you might have studied at the undergraduate level. So, let us see how it fits in, and then we look into the control system, right. So, what is a system? Well, system can be broken down into smaller components. They can be studied independently and then integrated, that you might be knowing, might have come across somewhere. Services can be considered as a system, because it has different component and they can be studied independently and put them together. Now, this is what it is. You have some input into the system, some input into the system. Here is the system and you get some output, right. Now, as far as service systems are concerned, you have an overall environment which includes the building as a whole, because service system, this output goes to the building. So, its overall environment might be building, might have flow system, usually like water supply, electricity, even waste disposal, everything is basically, or air flow system, HVAC, these are all flow system. So, you have a resource environment in such one, and you have a control environment. For example, you might be this might be HVAC. If I consider, it would supply cool air. If it is cooling, then it will supply cool air, draw some resources. In this case, resources would be energy, draw some resources, and in some cases it could be material also. For example, in water supply system, it draws the materials and also energy, and then work onto it, and then it supplies this to the control environment. Now, control environment is nothing but the space, the room. Control environment is a space, room where I need them. So, generally they are flow system. The component should be a resource environment, obviously service system would be there, and then it works onto those resources and supplies the modified in some form, the modified some material, or it could be fluid to the control environment, and maintains a control environment in the right condition that we desire. So, that is what it is. So, therefore, this is what it is. So, if I call this as resource environment, this is my control environment, which is again room, this schematic. There will be some secondary outputs, right. Secondary output, for example, you might it could be secondary output could be some heat losses, or even some sort of say it generates some sort of maybe like a boiler. For example, earlier days we were using coal fired boilers, so it would generate some sort of gases after burning. So, secondary outputs could be desirable or not desirable. You might be able to use those secondary output somewhere else if it is desirable, and then there will be some perturbation from the surrounding environment also. The control environment will get disturbances from outside. For example, outside temperatures would change, would affect the inside condition, so there can be disturbances. So, what we see overall is a kind of a, if I look it in a bigger way, so okay, we will look it in a slightly bigger way, it's something like this. I have some sort of a resource environment. The resources would be materials, energy, whatever it is. Then I have the service system. You know, this service system takes this, draws these resources and handles it in some manner, processes it, and this resource, processed resources then pass on in some form some resources to the control environment, right. And it can have perturbations from outside, you know, some sort of outside disturbances, some sort of outside disturbances could be there, some sort of outside disturbances could be there, disturbances from outside, and also you might have some sort of secondary disturbances could be there, secondary output also might be there, some secondary output also might be there. But then this secondary output coming from this, you might be using this as resource for might act as a resource for some other service system, because there are several service systems in a building. Actually, building is the most complex. I do not know whether I have mentioned this earlier to you. It is the most complex of the infrastructure. If you look at bridges, you know, let's say okay, steel concrete composite bridge, right. You have piers and then 10 piers. So they are all same, right. The deck system might be a composite slab deck with steel plate girders, composite made into composite. That is the whole structural system. Then you have service system, of course, there also, like lighting, signal system and things like that. So that is there it ends. Dams will be something similar. Of course, dams you have monitoring also, but come to building, it is actually very complex, because it has too many items. A hospital building might, cost of the services might be much higher than structural cost. Structural cost may not be more than 20-25%, at best 30%. Cost of the lift, cost of the electricity supply system, the hot and cold water supply system, the plumbing system altogether, cost of maintaining the sterile condition or some oxygen supply system and things like that. So, the cost in a hospital could be, services cost could be very, very high, and handling the waste. So, you might end up, and also the architectural items, you might end up with some lakhs of items in a building, unlike many other civil infrastructure, right. So, it is far more complex than many of them, and so you have different services systems. So, one output from secondary output from one service system might act as a resource for another system. For example, heat loss from some system, you might use it again, you know, recycle, use it and so on. So, this is all possible, the more general case. So, this is how this diagram shows you that you have, you know, this same resource might be used by two systems, same resource must be used by two systems, one resource, same resource might be used by two systems. So, more general scenario, and this is output from one system goes directly to the control environment. And then lastly, you might have a feedback. Okay, so, this is again, this is, you know, the secondary output going as resource to the second system. So, all combinations are possible here. Now, then you can have a feedback, which we will discuss later on. You know, for example, you want a control, then you might provide a feedback. So, this is your resource environment, this is your control environment, and you want you know, there might be flow is somewhere here from this one to this. So, you might provide some sort of feedback to this. If you want this control environment to be 100% under control, fully controlled, then you can have a feedback. So, if you have a feedback, some system feedback system, which would, you sense the putting sensors onto your space and providing feedback, and then have controls on this, the flow level or supply, to the service system might be controlled. Finally, this has to be controlled. So, finally, so basically, extreme case would be what is called an intelligent building or smart building, where you have a lot of controls. Some of it we will be discussing, but just as an introduction, I just told you. We will come back to this actually, this control later on when we talk of control environment more. Now, flow systems, two laws are very common, or similar laws are there. One is a continuity, right? One is a continuity, and another is continuity. So continuity is like Kirchhoff's law or any law for that matter. At any joints, you will have, so in such flow system, you will have basically some sort of a circuit, some sort of a circuit. So you will have, network of connectors, and at any junctions you will have two things. There is a loop, there can be a loop, and there can be junctions. So inflow at any junction should be same as outflow. That's what is your like continuity equation. So coming, it's and the other is so there are two types of variables one can recognize. One we call as flow variable, other is across variable, because to have any flow, I need a potential difference. For current to flow, I have electric potential difference. For sensible heat to flow, I need temperature difference. For flow of water, I need head difference or pressure difference. So there is like, so across, this is nothing but across variable. So across variable and flow variable. So flow variables are I, Q, etc. We denote generally by I, current, Q, flow, rate of flow. So across variable is basically the driving potential, more or less generalized law. So temperature difference, potential difference, pressure difference at any node, this is I5 actually. At this node, I1 is equals to, at node A, I1. So generalized one would talk about at any node incoming flow must be equals to outgoing flow, right. So that is one type of flow. So in a closed loop, sum of all across variable must be equals to 0. This is the other law, that is, if you measure in a systematic manner, the sum total of across variable from A to C, C to B, and B to A must be equals to 0, because at this point when I come back, it must be equals to 0. Now thing is that across variable A to C is equals to minus across variable C to A. So I write it like this: A variable say theta, A theta. This is in this one I am writing it in this manner. AB, so AB plus BC plus CA must be equals to 0. While we understand that CA is nothing but minus AC, CA is minus AC. So this is one aspect. So this is the law for almost all flow system. This will be the law. We will see that how it applies, where it applies. These are Kirchhoff's laws actually. Second one is also Kirchhoff's second law, no? First one, so you might call it, is it compatibility? Not really. This is continuity for sure. That's continuity law. So, okay, so that's general. That's basically very general. The other issue is most important thing for almost all services, because it's dealing with the human being, right? Dealing with the human being, right? Dealing with the human being. So we organize our activity in 24-hourly cycle. That means every day you go to the office at maybe 9 a.m. right. So 24-hourly cycle. So that's we look everything into, we will have a usually 24-hourly cycle. So any demand on the service is also 24-hourly cycle. I mean, I might have, for example, the classroom, right. So my cooling requirement might start from sometime around 8 a.m. in the morning, or maybe 7:30, because you might put it on earlier, supposing it's 2-point open control switch or whatever it is, and then it will finish off by 5. But after that, no requirement, again it starts at 8. So it's again 24-hourly cycle. For certain period of time I have the demand, for certain other period of time, but it's a 24-hourly cycle, and everything else is also similar. So services also we have 24-hourly cycle, 24-hourly cycle, and it could be something like this, it could be something like this. I can think in terms of demand rate, demand on anything, right, the electricity, cool air. So it will fluctuate from time to time in the day, and then after a time period which is generally 24 hours, again it will start. So I can think in terms of a 24-hourly cycle of demand for almost everything. So this is more generalized, that's what I was saying. And in this one, it may so happen that my demand rate, of course, as you have seen, it will vary. I mean, it can be simplified, could be something like this, it's possible, right. But usually demand would vary, usually demand would vary very in arbitrary manner as we have drawn, but some manner it will vary. Now if it varies, I must, if I match the supply exactly with that, then I don't need any storage. But it is difficult to match exactly with that, I cannot match it, I will not be able to match it. So usually where there is a demand, or in the part of the system itself, if there is a mismatch between demand and supply, I need some sort of storage. So that means, for example, you have resource environment, some component within the service system and some other component within the service system. Now it draws the resources from component 2, draws resources from component 1, and its demand would depend upon the final demand of the control environment. Now it may not match, matching exactly with the supply rate might be difficult, rather I will provide as kind of storage. Whenever I need, I will actually draw it, whenever I need, I will actually draw it, whenever I need, I will draw it, right, and store it. But if I store it too much, then the cost of storage will increase, right, and or cost of supply might increase if I actually try to match exactly. So we try to do a balance, so when do I need storage? When there is a mismatch between demand and supply. So I provide a storage. For example, you can look into this is a cold water to hot water supply system. Now this one is a heat exchanger where I will be heating the cold water, right, and it will be drawn. Now hot water demand would be varying, it would be fluctuating. So if it is fluctuating, then here I might store. At the top level, hot water will be there, cold water enters at the bottom, because convection it will put it up, right, and the capacity of this system storage would depend upon how is the mismatch, but I can't go on infinity, because if I do it, the cost of storage will increase. So we try to optimize this between two things. One, try to change the supply rate, choose a supply rate which would, and the cost of supply also depends upon the supply rate itself, because your network cost would increase depending upon what is the pipe sizing, if it is pipe case or things like that, insulation in case of hot water and all that. So network cost will increase depending upon the supply rate, and storage cost will increase if I increase the size of the storage. So I try to balance between the two and design it, and let us see how we do it, right, design it in this manner. So, this is another example. For example, I might have hot water here, same one, diagram is different, hot water is here, cold water is here. So, capacity of this heat generator or heating element or whatever it is, this also would depend, because rate, this is related, I mean finally this will be in terms of hot water means some energy also. So, mass into specific heat into the quantity of hot water that is available. So, it will depend upon how much is my demand onto the system. So, during I can think in terms of during time period T total demand must match the supply. This must be the case all the time. Might have some small amount of buffer, but by and large it must match. Otherwise, what will happen? If my demand is more and supply is less, obviously I will fail, my system will fail. And if other around, if the store, if the supply is more, demand is less, then I will be continuously go on storing, and my like storage will burst or whatever it is, it will overflow. So, therefore, it must match in some manner. So, mathematically simply one can write, if I define supply as S theta, d theta, and demand is d theta, during the time period my cycle, this must be matching, this must be matching, this must be matching, right. So, you can this must be matching, and therefore, demand will depend upon usage pattern, as we know. Demand depends upon usage pattern, and hence difficult to control. Demand is according to the usage pattern, depends upon occupancy type, and some case of randomness also might come in there. Some sort of randomness also might come in there, and it is difficult to control. So, what we try to do? We maintain a constant supply which is cheap. For example, supply rate is constant. I might supply for certain period of time, then stop, and then again supply, or I can have a continuous supply, right. So, my rate of supply is constant, usually we maintain, because it will be otherwise costly depending upon the cost part of it, and maintain it constant supply. So, what is the minimum constant supply? That I can find out. Minimum constant supply would be minimum cost, So, finally, of course, I can always talk in terms of cost of supply. Supply is a function, cost of supply is a function of rate of supply, that I already mentioned. If rate of supply is higher than rate of demand, there will be required storage, which leads to storage cost. So, we need to minimize the total cost, which is composed of cost of supply and cost of storage. So, we are trying to get a model for this kind of a scenario, right, and storage would depend upon difference between these two. If they match during any period of time, cumulative supply and cumulative demand, difference between these two, up to that period of time, whatever is the difference, that I must store, and that is actually y theta, let me call it, that I must store. Storage will depend upon this, and if I write it dy d theta, differentiate this, then I will get S theta. So, the place where storage would become 0 would corresponds to where supply rate is equals to demand rate, supply rate is equals to demand rate, right, where supply rate is equals to demand rate. Now, what is the minimum supply rate? Because we said that over the time period S theta d theta must be equals to d theta d theta, over the time period they must be same. So, minimum supply rate, and I am keeping my supply rate constant. So, minimum supply rate is simply this divided by time period. The minimum supply rate, just let me write it separately. Minimum supply rate would be d theta 0 to t 1 by t, that will be a constant supply rate, is not it? Because my supply rate, this is the total supply I require during the time period, and my total demand. sum total of all the demands, total cumulative demand during the time period, and this must match with the cumulative supply during that period, right. And if I have a constant supply rate S, then S multiplied by T must be equals to this, because it is constant, it is not varying with theta. So, 1 by T average, simply averaging the demand rate, that would give us, right. So, that is what it is. So, simply graphically you can find out like this, which you might have done, sometime you might have done in water supply system, but essentially it is like this. So, this is my period, 24-hourly period, cumulative demand I have plotted like this, which will go on increasing, which will tend to become a S curve sort of, right, which will tend to become a S curve sort of. And if I join like this, constant supply, you know, or this is the demand profile, the area under this curve is this much. If this divided by T, this area is same, this rectangular area is same, because S into T is equals to, I said, area under this curve, integral 0 to T d theta, you know. So, integral, so area, this is cumulative. So, at any point of time if you want to find out, it will be theta. So, basically constant supply rate I can find out if I sum up all the demand over 24 hours divided by 24, that will be the constant supply rate which I must maintain. If I supply lesser than that, I will not satisfy the total 24-hourly demand. So, that is the minimum constant supply rate. Now, I can increase the supply rate, but do not supply for 24 hours, depending upon my convenience, right, depending upon my convenience. So, what I do is I stop in between, these gaps are there. So, I can have intermittent supply, increase the supply rate, have intermittent supply, and do it in such a manner that my storage gets reduced. So, I will find that supply rate I increase, storage should reduce, I choose it in that manner, and I will have several storage and corresponding supply rate, several supply rate and corresponding storages, right, several supply rate and corresponding storages, and then I find out the best out of from them, right. So, that is what it is. Yeah. So, I think we will stop. Next class we will look into this model.